Hello everyone, I am Rohini Haridas, working as an assistant professor in Electrical Engineering Department at Maulana Mukhtar Ahmad Nadwi Technical Campus, Malegaon. Today in this video, we are going to discuss about the universal torque equation and phasor diagram for directional element. The objectives are to study the universal torque equation, to know the directional characteristics of the relay using phasor diagram, and these are the some possible outcomes. After watching this video, the learner will able to describe the operation of the relay using universal torque equation, define the maximum torque angle, and explain the directional characteristics of the relay using phasor diagram. Now let us see the universal torque equation. We know that the most of the protection relays consist of some arrangements of the electromagnets, which carries current coil, voltage coil, or the combination of the both. The operation of such a relay is explained with the help of universal torque equation, and it is given by T is equal to K1I square plus K2V square plus K3Vi cos theta minus tau plus K4. Here K1I square is torque developed by current coil, K2V square is torque developed by voltage coil, K3Vi cos theta minus tau is torque due to the directional element, and K4 is the torque due to the spring. Here theta is the angle between voltage and current, and tau is the maximum torque angle. In this equation, K1, K2, K3 are the constants. Now each coil will produce the torque. If the torque produced tends to close the trip contact, then that torque it is called as operating torque, and the torque which tends to oppose the closing of the trip contact is called as the restraining torque. We know that the relay will operate when operating torque is greater than the restraining torque. The operating characteristics equation of the all types of relay can be obtained using the universal torque equation. Here you have to just assign the positive and the negative signs to the certain constant depending upon whether the quantity it is providing operating torque or the restraining torque, and let other constants be 0. So in short, the quantity which provides the operating torque assign positive sign, the quantity which provides the restraining torque you assign the negative sign. Now let us consider the case of overcurrent relay. In overcurrent relay, the operating torque will be provided by the current coil and the restraining torque will be provided by the spring constant. In the overcurrent relay, the K2 and K3 will be equal to 0 because of the absence of the voltage winding. Now let us consider the universal torque equation. In this equation, because of the absence of the voltage winding, the term K2V square will be equal to 0. Similarly, the term K3Vi cos theta minus tau will also be equal to 0. That is, no directional element will be present. Now here the current element will provide the operating torque, and therefore you assign the positive sign. Similarly, the spring constant will provide the restraining torque, so you assign the negative sign, and therefore the torque equation will be K1I square minus K4. Now let us consider another example of simple impedance relay, in which the current coil provides the operating torque and voltage coil provides the restraining torque. Let us rewrite the universal torque equation. In this equation, the current element provides the operating torque, so you assign positive sign to K1I square term. K2V square term provides the restraining torque, so you assign the negative sign. Here the directional element is absent and therefore K3 Vi cos theta minus tau term will be equal to 0. Also K4 provides the restraining torque, so you assign the negative sign. Thus the torque equation becomes T is equal to K1 I square minus K2 V square minus K4. On the verge of operation, the torque due to the spring can be neglected, and therefore the final equation will be T is equal to K1 I square minus K2 V square. Now let us study the phasor diagram to understand the directional characteristics of the relay. Let V be the applied voltage to the relay through PT and it is a reference quantity, and I be the relay current through CT. The system current is generally lagging the voltage, but with suitable connection the relay current is made to lead the voltage by an angle of theta, and therefore in the figure current I is shown leading the voltage by the angle of theta. Here phi V is the flux due to the voltage coil and it lags behind the voltage by an angle of phi. Similarly, phi I is the flux produced due to the current coil and it is in phase with the current phasor. We know that the torque is produced because of the interconnection of the two fluxes. That is, here the torque is produced because of interconnection of flux produced due to the voltage element, that is phi V, and flux produced due to the current element, that is phi I. Therefore, T is proportional to phi V phi I into sin phi plus theta, where phi V is proportional to the voltage and phi I proportional to the current. The torque is maximum when the two fluxes, that is phi V and phi I, are displaced by the angle of 90 degree. That is, when the theta plus phi is equal to 90 degree. So here the dotted line in the phasor diagram represents the desired position of phi I, that is nothing but the maximum torque line. Here the V is the reference quantity and therefore phi V has fixed position with respect to the voltage for a particular design. So the angle between the dotted line and the reference quantity V is known as the maximum torque angle and it is denoted by tau. Now the zero torque will occur when sin theta plus phi term will be equal to 0. That is, phi plus theta is equal to 0 degree or 180 degree. This being satisfied when the relay current phasor lies at right angle to the maximum torque line, and thus the directional element will provide the current phasor lies within the plus minus 90 degree of maximum torque angle. So here you can see this is the zero torque line and the operating region as well as the restraining region, or you can say it is the non-operating region. The directional element will operate provided that the current phasor lies within the plus minus 90 degree. You can see in the figure, if it is displayed more than the 90 degree, then the element will restrain. That is, in the figure it is shown by the non-operating region. Now let us see what do you mean by the maximum torque angle. The angle between the voltage and the current at which the relay develops the maximum torque is called as maximum torque angle and it is denoted by tau. From the figure, we can write phi is equal to 90 minus tau and let this is equation number 1. Also we know that the torque is proportional to phi V phi I sin phi plus theta and let it is equation number 2. Now putting equation 1 in equation 2, we will get T is equal to k phi v phi I sin theta plus 90 minus tau. Here the sign of proportionality, it is replaced by the constant k. So finally we will get T is equal to k phi v phi I cos theta minus tau. When you refer the universal torque equation, you can see this term, that is the element which produces the directional torque. These are the references.